All right, so today we're going to be talking about arc length. And arc length is just like, it really isn't bad. It's just like what we did when we were doing from Calc 1. Remember how you found the area, you found the tangent, and when we found the integral, what we ended up doing was taking different segments along the way to find our tangent line. Do you remember that from Calc 1?
Yes.
Okay, so it's the exact same thing that we're going to do here. So I'll show you guys a picture, and then we'll talk about how they derive this integral that we have for arc length. So if I have a curve like this, right? To find the arc length of this, we'll call this point pi minus 1, and this one over here we'll call p, or we can call it pi if you want. And what we're going to do is we're going to take tangents, or I'm sorry, secants, to go ahead and find out what we're getting. So this secant would give us an approximation of the arc length. Do you think that's going to be a very good approximation?
No.
Yeah, the answer is going to clearly be no, right? So what we end up needing to do is we need to be able to do more and more movements. And so what we'll do is we'll take the curve and put in another dot, and then when we approximate this, we're going to go this to this, and we can see that that's going to be a slightly better approximation than the first one we did, right? Well, we can do infinite number of these, and guess what ends up happening to our approximation of the arc? It becomes super accurate, right? Does that make sense to you?
Yeah.
Okay, so here's the math behind it. So going back to geometry, we have what's called the ruler postulate. And the ruler postulate tells us that the distance between 2 points is simply the square root of the differences of the coordinates, correct? Correct? But if we have a difference for our x values from one point to the next, isn't that just a delta x, or a change in x? So can't I write that as delta x squared plus delta y sub I squared, right? Isn't that one and the same?
Yes. Yeah.
Okay, and then from Calc 1, by the mean value theorem, we know that f of x sub I minus f of x sub I minus 1 is equal to the derivative of x sub I star x minus x sub I minus 1. Correct?
Correct.
Okay, now here's the important critical piece. Isn't this simply the change in y? And isn't this simply the change in x?
Yes.
Right?
Yes.
So then we're going to get delta y sub I is equal to the derivative of x sub I star, right? Delta x. Well, in the equation that we have delta x, delta y sub I squared. So instead of sorry, I gotta put my phone on do not disturb. I should have done that earlier. My apologies. Okay, sorry. So instead of writing the delta xi x sub y sub I squared, I'm going to rewrite that as the root of delta x squared plus, now instead of this, I'm going to put this in its place. We okay with that?
Yes.
And then that has to be squared. So then what we can see here is we're going to be able to pull out a delta x. So we're going to get 1 plus f prime of xi star, that quantity squared, under the root with a delta x on the outside. We okay with that?
Yes.
But what's happening,
Yes.
is we're moving closer and closer and closer to our p sub I. So that means that we have a limit that's occurring, correct? So our limit of this p sub I to pi is going to be equal to the limit of this root of 1 plus x sub I star squared delta x, which is the definition of the integral which is our arc length. Does that make sense?
Yes.
Yeah, it's just simple. It's just simple substitution. It's nothing too crazy. And really, the reality is you're not going to really need that. If you have this down and know how to use this, you're going to be gold. Chapter 8 is really pretty simple if you have your integration techniques down. So my suggestion is don't get yourself stressed. You should be able to be successful with this, okay? So let's do an example for this problem, okay? So in this first example, here I'll leave this just in case people are still copying. In this first example, it says find the length of the arc of the semicircle parabola y squared is equal to x cubed between the points 1, 1 and 4, 8. Well, we notice that in the equation that we have, and I have it right there, but I always want to write it down so you guys can have it, and so that it becomes something that you start to remember. It looks like I need the derivative with respect to x, right, in this problem. And so I could go find that implicitly and then do a substitution, but that just seems like a lot of work. So what I'm going to do is, instead of having y squared is equal to x cubed, I'm going to change that to y is equal to x to the 3 halves. Okay, that's the same equation, correct?
Correct. Yes.
Okay, just making sure. So then when I take the derivative of this, I'm going to get dy is equal to 3 halves x to the 1 half dx. Yes?
Yes.
Okay. Now, since we're doing it with respect to x, the arc length, the integrands are going to go from where to where? It's okay if you say no.
Would it be from 1 to 4?
It's from 1 to 4. And the reason it's from 1 to 4 is because we're looking at the x's. So we're looking at the x coordinates. If we had done it with respect to y, it would have been from 1 to 8. Okay? Now, the integral then is going to go the square root
I have
of...
a question.
Yes.
It's just to confirm, we're doing it to the respect of x because it's f prime of x, right?
Correct.
Okay.
But we could make it f prime of y. I'll do a problem like that later, just so you can see it. But right now we're doing it with respect to x.
Okay, just trying to see where everything correlates. Thank you.
Yeah. The thing is there'll be times where the integral will be easier to deal with in terms of y than x. So that's where, now that you guys have these techniques, you need to decide which is easier. So more responsibility falls on you. Yay, right? Okay, and then the derivative is going to be squared. So I'm going to go 3 halves x to the 1/2 squared, and then dx is going to be on the outside. And really the way I should write this, so I'm consistent for you guys, is this way. Because that's our prime. Okay? So now to simplify this, I'm going to go, okay, the integrals from 1 to 4 of 1 plus 9/4 x under the root dx. Does everyone agree with that?
Yes.
Okay, now we need to integrate this. So how can we integrate this problem? What would you do? I'll wait.
Would it be a U-sub?
That's exactly it. It's a U sub, Miranda. Good. So we're going to go U is 1 plus 9/4 x. We could have factored out a 4 and then had a 1/2 in front and then done a U sub from there, but there's no sense to that. So du is going to be 9/4 dx. So then 4/9 du is my dx, correct? Now, from here, what I want to do is I'm going to change a bunch of stuff. So I'm going to change my bounds, okay? When I change my bounds to this thing, I'm going to have a 4/9 in front, right? That's because of this right here. And then my integral is going to be the integral of u. And then I'm going to have du. But my bounds are going to change because I don't want to go back to x's. I'm going to change my bounds. So when I plug in 1, my lower bound is going to become 13/4. And my upper bound is going to become 10. Are there any questions on how I got that?
Yeah, could you explain that, please?
Sure. So plugging into this right here, I'm going to use my lower bound. And my lower bound is going to be, u will be equal to 1 plus 9/4. And then I'm going to plug in 1. And then when I plug in 1 there, what's going to happen?
You have to change the 1 by itself to 4/4 fraction.
Yeah, we'll see that becomes a 13/4, right?
Yeah.
And then when I plug in 4, I see that I'm going to get 1 plus 9, which is going to give me that 10. Does that make sense?
Yeah.
Yes.
Okay, just making sure. That was you, Jason, that asked that, right?
No, it was me. Aaron.
Oh, Aaron. I always mix you guys up. That's funny. I'm sorry about that. Okay. I'm going to actually know you guys better by your voices than I'm going to know you by face. That's crazy. Okay, so then now I need to integrate, right? So when I integrate this thing, it's u to the 1/2, so I'm going to get u to the 3/2. There's going to be a 2/3. That's going to be multiplied by 4/9. And then I'm going to evaluate that at these values, correct? So that's going to give me 8 over 27. And then I'm going to get 10 to the 3 halves minus 13 over 4 to the 3 halves. And then that's going to clean up for me nice. I'm going to get 1 over 27 with 80 root 10 minus 13 root 13. We okay with that? That's just arithmetic.
Yes.
But I want to make sure you guys are okay with it. There's nothing that's overwhelming or confusing about that. And this is our solution. Right, and since this is a, what's interesting about this is this is arc length, this is one dimension, okay? So if it was in meters, it'd be in meters, because the root does that for us, right? So we are in whatever units of length, because the length is just one dimension. Does that make sense to everybody?
Yeah.
Okay. May I move on to the next example?
Yes.
Okay. All right, so let's look at this one. It's kind of the same thing, but what we're going to find here is it says find the length of the arc of the parabola. Y squared is equal to x, and we're going from 0, 0 to 1, 1. And we know it's going to look like a rooted function, right? So when we look at this, if we were to take the derivative of this and we were to go, all right, let's do the same, my apologies. We did the same strategy that we did before, we'd have this, correct? I just want to show you something. If I took the derivative of this, dy dx would be 1/2, and then the x is going to end up in the denominator, correct? So I would end up with 1/2 x to the 1/2 power. Agreed?
Agreed.
Okay, so look at what happens here. If I do this, I'd have an integral that would go from 0 to 1, because we're talking about the x's, of 1 plus 1 over 2 x to the 1/2 this quantity squared dx. Well, that gives me the integral from 0 to 1 of 1 plus 1/4 x dx. Does that look like something that's easy to integrate? Do we have techniques to be able to attack this problem? Is it something that you guys see that you could do easily? How about that?
I mean, could it be an x to the negative first power?
Okay, well, if we have an x to the negative first power under a root, how do we integrate that? Is it something that's simple? So it's important to realize, all right, is it simple, right? So let's manipulate it a different way and see what happens. Let's say that I said, all right, I don't really like the way it's set up, so I'm going to do this. I'm going to say 2y is equal to dx dy, and now what I've done is I'm taking the integral with respect to y, right? So I want to see what happens if I take the integral with respect to y, if it's going to be easier. Well, now the integral, right, the arc length integral is still going to go from 0 to 1, because unfortunately in this example, the y values are the same as the x values, correct? We're going to get 1 plus 2y squared rooted dy. Is this an easier integral to do?
Yes.
Yeah.
Yes. By far.
It's much, much easier. So whenever you're doing these problems, you're going to want to think about, do I do it in terms of x or do I do it in terms of y? The integrals that are easier are going to be the ones you're going to want to do. So, it's a derivative, no big deal, but you can check the derivative both ways and say, all right, which one's going to set me up to be easier? And clearly in this case, doing it with respect to y is going to make my life so much easier. Now, this problem still isn't easy. We still have to know techniques. By looking at this, we know that this is a trig sub, right?
Right.
It's a trig sub. Can anyone tell me what trig sub this is?
Is it tangent?
It's tangent. Very good. So then what we're going to do is we're going to go, okay, y is equal to, I'll do it this way. 2y is equal to tangent theta. But to make my life easier, I'm going to go 1/2 tangent theta. And so when I take the derivative of this, I'm going to get dy is equal to 1/2 secant squared theta d theta, correct? And then what I'm going to do is I'm going to take the integral. Now, I'm not going to change the bounds because with trig subs, it can be ugly. So I'm going to go back by making a triangle and doing all that stuff. But I want to show this to you guys so you guys can see it. So I'm going to get 1 plus 4. And then I'm going to get 1/4 tangent squared theta under the root times 1/2 secant squared theta d theta. Right? That's going to equal the integral of secant theta, I'll put the 1/2 out front, times secant squared theta d theta, which is going to equal 1/2 the integral of secant cubed theta d theta. But we know that guy. We've done that guy before, right? This is the secant cubed. I'm going to skip the steps because it's an integral that I did in the last chapter. But we know that secant cubed is going to be a repeater, correct?
Right.
Right? So I didn't obviously put the space to do it. If you want me to, I can. I can do it at the bottom, but I'm just going to jump to it. I'm going to get 1/4 the integral of secant theta times tangent theta plus the natural log of secant theta plus tangent theta. And then now what I need to do, and in fact I probably should have written this up here. In fact, is it okay if I go up here with it? I'm just going to need this space. Now, what I need to do is reference a triangle, right, to be able to find out what it was. And so the triangle that I'm going to reference is going to be based off of this right here, correct? So I'm going to draw a triangle. Here's my theta. So tangent theta is 2y over 1, right? So tangent is opposite over adjacent. So this will be 2y. This will be 1. And this up here will be 1 plus 4y squared rooted, right? Do we agree?
Yes. Yes.
Okay. So then from here, I'm going to get 1/4. What is secant? isn't secant the hypotenuse over the adjacent then? Because it's the reciprocal of cosine?
Yes.
So I'm going to get 1 plus 4y squared rooted over 1 times tangent, which we know is 2y, plus the natural log of secant, which is that 1 plus 4y squared, plus 2y, right? And now we're back in terms of our y's. So now we can evaluate, and the evaluated integrands were from what to what?
1 to 0.
From 0 to 1.
1.
So when we plug in 1, I'm going to get 1/4 square root of 5 times 2 plus the natural log of square root of 5 plus 2 minus, when I plug in 0, I'm going to get 0, and I'm going to get 0. So this will be 0, and then my final answer is going to be 1/2 root of 5 plus 1/4 the natural log of root of 5 plus 2. So I wanted to show you some steps in this problem, but you can see chapter 7 is not going away. You're just basically going to be doing more and more practice with it here. Okay? Any questions on this problem? No? Or are you guys just right now just trying to absorb it?
Writing and absorbing it.
Yeah, no, I get it. Am I going too fast? If I am, just let me know. I don't want to overwhelm you guys. Did you guys finish copying it?
Yes.
Yeah.
Okay. So the setup for this one is look at the derivative, decide which derivative is going to be easier to set up your integral. Sometimes it will be with respect to x, sometimes it's going to be with respect to y. So it's just a matter of deciding which is the easier integral. Just so you guys know, this is terrible. I would not go that route. It's a wormhole that you don't want to go in. Right? Okay. Next problem. And you can tell that this one already, the integration is going to be somewhat difficult because they're not asking you to do the integral. They're asking you to set it up, to see if you can set it up correctly. So let's look at it and we can decide, is it going to be easier to do it in terms of dx or dy? What do you think?
I think dx.
Yeah, it actually ends up being the same thing because whenever you solve for either one of the variables, you're going to end up with 1 over x or you're going to end up with 1 over y. So either one is going to be the same thing. So let's just solve for y because it's what we're used to doing. So we'll be like y is equal to 1 over x. So when I take the derivative, I'm going to go dy dx is equal to a negative 1 over x squared, correct? And then to set it up, since we're doing it with respect to x, the integral would have gone from 0 to what? Oops, not from 0. From what to what?
1 to point, wait.
1 to 2, right? Because we're looking at the x's. And so then we'll have our root 1 plus a negative 1 over x squared dx. Okay? And then if we wanted to clean it up, we could clean it up, which I'll just show you. And then you can see how this becomes an ugly integral. Now, we could clean that up just a little bit more, and the integral would have been, I can write it right here. So in order to do this integral, if we wanted to do this integral, what do you think you would have done? What method would you use to attack this?
Would it be integration by parts?
The root throws us though.
Would it be a U sub?
Well, if we did a u sub, then we'd have to solve for x squared. So look, I just want to show you because that's cool. What would be the u sub if we did it that way? I just want to take you guys on a little journey real quick. What would you make your u?
X?
It'd have to be something more than x.
X squared?
The fourth plus 1.
Well, if the x squared, I mean, if we did x squared, we run into an issue, right? If we do x squared, look what happens. I go du is equal to 2x dx. Where do we have an x to eliminate? Does that make sense?
Oh, yeah, I see. Correct.
So let's say that we do, all right, what's under the root, right? So u is x to the 4th plus 1. So we'd be like, okay, we have 4x to the 3rd dx. But now we have an issue, right? Some games we could have played, we could have gone 1 over x squared du is, I should have brought the 4 over. I mean, there's some crazy things that we could play, but we can see that this ends up being, u is going to be problematic, right? As we start to try to play things. So that won't work. But one thing that might work is, what if I had x squared plus 1 rooted over x to the square? Couldn't then I do a trig sub?
Yeah.
And then it'd be a tangent. So I just wanted to show you guys, all right, how to decide how to attack this problem. You're going to try all your techniques, right? It really is trial and error. You just need to see, all right, u didn't work. U for x squared didn't work. U for x to the 4th plus 1 didn't work. Okay, what can I do? A trig. If it's a trig, then I have to have it in terms of squares. Is that going to help me? And we can see that it really will. But again, it's a tricky little game to play. But I just wanted to take you through the thinking that goes behind it, so that you guys can see how to go about doing a problem like that. Now, fortunately, in this example, it's not asking us to do it. It's just asking us to set it up, which we did right here. Now, it's asking us to use the Simpson rule to be able to find the arc length. Now, do you guys remember the Simpson rule?
It's delta x over 3 times
Yeah,
f of
1 and then 4, 2, 42421, right? So what's our A in this case?
Two.
The A is 1.
Oh,
What's our B?
two.
2. What is our N?
10.
Perfect. 10. And then our delta X, isn't that going to be 2 minus 1 over 10, which is going to give us 1/10? Right? So then when we do Simpsons, S sub 10, I'm going to get 1/10 over 3 of f of 1 plus 4f of 1.1 plus 2 of f of 1.2 plus 4 of f of 1.3 dot dot dot, right? Till we get to the end. And then S of 10 will approximately be those summed up. And you plug in to get your F1, F1.1, 1.2 into this equation here. That's important. That's where you're plugging in to get F1, F2, F3, F4. Does that make sense?
Yes.
All right, that's important. And then your answer ends up being 1.1321. But it's the process behind it that matters, okay? Can you set up a arc length integral? And then the other is, do you remember your Simpsons rule to be able to do it that way? Any questions on this one? Crickets? Don't worry, I'm not going to give you a bunch of homework. After our class is done, I'll put up the homework, but I'm sure, I think it's under 10 problems, so it shouldn't be an issue. In fact, let me check real quick. You know, I said to you guys that I was going to put this up as a video, and for some reason I don't like doing that. I feel bad for you guys with me just putting videos up, because if I do that, then you guys end up not being able to ask questions, and I feel like that's such an important part of this class. So that's why I don't do it. Would you prefer that I put up videos beforehand?
Like before the lecture?
Yeah. Or do you guys prefer just...
What's that, like you doing double work?
Well, I mean, yes, but I mean, it's only for this first semester that I'm teaching this class. After that, I won't have to make the videos again. There's only 8 questions on the homework. So yeah, I'm not trying to mess you guys up. I just want to be able to help you guys as best as I can. And there's moments where I'm like, I mean, you know, there's 30 some people in our class, and there's 15 of you in here. So it's like, all right, how can I best serve the class? Because obviously half of you are just watching the recordings. So that part makes it hard. But all right, well.
Well, I think it kind of helps, like, in case you can't make it, and like when you watch the video, you basically can see the step by step instead of just seeing the notes where you just bunch of writing, you know.
Yeah, I mean, I still put up the recordings, like right now, this recording that I'm doing, I put up. But what I'm asking is, would you prefer just to be me without any questions from you guys? Or do you prefer it to be able to see me having you guys on and asking questions?
I like the way it's set up now with the questions. Because
Yeah.
sometimes other people have a question that I'm thinking and you kind of answer it.
Mm-hmm. Yeah. I tend to agree with that, because you're asking questions makes my lecture better, and it probably slows me down, because if I were to do this on my own, I mean, these videos would be like 30 minutes long and be like, you guys can pause and rewind. So you're probably right. It's probably better to do it with you as a class. All right, let me do this number 4, this example number 4. And then that'll be it for today in terms of what I have for you. And then I'll put the homework up. All right, so in this problem here, it says find the arc length for the curve. And now they're only giving us an initial point. And so since they're giving us an initial point, we need to come up with an arc length function. So when we take the integral, it's going to be a function to find the arc length no matter where the endpoint is. Does that make sense?
Yes.
Okay, so let me show you this. So the first thing I need to do is I'm going to take the derivative. So I'm going to get dy dx is going to be equal to 2x minus 1 over 8x. Agreed?
Agreed.
Okay. The integral, I don't know the upper and lower bounds, so I'm not going to mess with that yet. I'm going to try to clean this up. So I'm going to get the root of 1 plus 2x minus 1 over 8x, that quantity squared, dx. Then I'll clean this up to be 1 plus 4x squared. The x's are going to cancel, minus 1/2 plus 1 over 64x squared dx. Agreed?
Agreed. Yes.
Okay. Then I'm going to get 4/2 x plus 1/2 plus 1 over 64x squared dx. And something cool happens. This happens to be factorable. So I'm going to get 2x plus 1 over 8x, that quantity squared, dx. And what I get is the integral of, oops, I don't need the root anymore. That's going to go. X plus 1 over 8x dx. But we're running into an issue, right? We know that the integral is starting at 1, but we don't know where it's going in terms of its terminal point. Does that make sense?
Yes.
And since we don't know that, what we're going to have to do is change our integral, change our variable to something in terms of, let's say in terms of t. So I'm going to say, all right, I'm going to now create my arc length function. And the way that I do that is I'm going to go from 1 to some terminal value x, some terminal point along the curve where I want to stop. But in order to do that, I can't integrate with respect to x. So I need to change those x's to some other variable. I'll call it t. Okay, so it's still the same function. It's just that the function is now changed to t, because when I take the integral to find the arc length, I'm going to be able to go from 1 to whatever that terminal x value is. Okay? Because that x value is going to be some concrete number. Does that make sense?
Yes.
Okay, so when we take the integral, I'm going to get t squared plus 1/8. What's the integral of 1 over t? Anybody?
ln of t.
ln of t, right? Should be an absolute value. And then we're going to evaluate that from 1 to x, right? From 1 to x. So then what I'm going to get is, oh, and this function should be s of x, right? S representing the arc function. So I'm going to get x squared plus 1/8 ln absolute value of x minus 1, right? Oh, and I can put the other one, which will be minus 1/8 ln of 1, but we know that the ln of 1 is what? 0. So then our s of x function is going to be x squared plus 1/8 ln of absolute value of x minus 1. Okay, this here, this s of x function is our arc length function from 1 to whatever our x value is. Does that make sense? This is
Yes.
specifically starting at 1 because that was our lower bound. If we were starting at 2 or at 3 or at 4, that lower bound value would have to be 4 or 3 or whatever number we're starting at. Does that make sense?
Yes.
Okay, it's important you guys get that because I might give you one that starts at 2, so that means your lower bound would have to start at 2. Understood?
Understood.
Okay.
Okay.
So now to be able to find the length, let's pick an arbitrary number, right? So let's say that I wanted to find out what the arc length is starting at 1 to 4. So then what I'm going to do is I'm going to go, okay, what is s of 4? Since I know I'm starting at 1, I've already got that. Let's plug in 4 and see what we get. So I'm going to get 4 squared minus 1/8 ln of 4 minus 1. Let me get my calculator. So I
Is
know
it
that's...
minus 1/8 or plus 1/8?
What's that? I'm
Yeah, why
sorry?
did it become minus 1/8? Shouldn't it be plus
Oh,
1/8?
plus. Thank you so much. Sometimes I get crazy, guys. I'm just, I make these mistakes to see if you guys are paying attention. Said every teacher that's a liar. I made a mistake.
Oh, you just chose 4 at random, right?
Yeah, I just chose 4 randomly. ln of 4 is 1.38629. And then minus 1, so that's going to be, let's see what that ends up being. 16 minus 1 divided by 8. ln 4 minus 1. I got... Did you guys get 14.8267? Oh, I messed up. I put a minus there again, so that's wrong. It should be plus. For some reason, the minus in front of the ln of 4 is in my head. So I got 15.1733 as my arc length. Did you guys get that too?
Yeah.
So when they ask you to go find a function and they don't give you a terminal, you're going to have to come up with the arc length function, okay? And the only thing that you're going to do is you choose an arbitrary variable. T is usually the arbitrary variable that we'll use. But then from there, your starting point to whatever you want the terminal point to be, you'll be able to plug into that function to find the arc length. Does that make sense?
Yes.
Okay. Does the arc length itself seem very difficult?
No.
It's not too bad itself. The problem is the techniques of integration that come into play, right? Those techniques of integration are so critical that chapter 7 is going to continue to come back and play. We're going to be doing trig subs, U subs, UV subs, partial fraction decompositions. Those are all going to come back to play. Fortunately for you, in chapter 9 we go away from that. In chapter 10 we go away from that. And in chapter 11 we completely go away from it. But these techniques are important for you to know for Calc 3. So practice, practice, practice. Okay?
Okay.
All right. Do you have any questions for me? Anything that you'd like to ask me about? Or do you want me to just get the homework up so you guys can get to it?
I want to start the homework.
Okay. So what I'll do then is let me stop recording. Boom.